Hello and welcome to Open Logic. In this series of videos, we're going to look at UVM, and this first video here will serve as an introduction. To understand the concept of UVM, we need to understand the concept of test. Say we have a smartphone as our design, and let's pretend it's a real hardware. In order to sell it, we need to make sure its functionalities are all okay, and for that, we need to test it. Imagine that we have a computer as our tester. It must support all the capabilities of the design. For example, the smartphone can support a Wi-Fi connection, Bluetooth connection, and USB connection. Once the connection is established, data can flow through between the tester and the design. If you're learning about system Verilog, one thing you should note is that we are not testing the real hardware. In fact, we are testing a model of the hardware that exists in a computer. And for the testing purpose, we also have a tester model as well. Now, let's try to compare between the actual hardware design and tester and their model equivalents. When it comes to design, a model is used to create an actual hardware, and therefore the hardware is pretty much matching to the model in terms of functionality, timing, area, and power. If a hardware deviates too much from its model, this is a problem, and eventually it will lead to low yield rate. And now let's move to the tester side. To understand the difference between a model tester and an actual tester, first we need to understand how an actual tester works. If we look at the computer, it has a CPU, various memories and storage which are connected through bridges or interconnect. And then there are various controllers and file components which are used to connect to the outside world. For example, this may handle Wi-Fi connection, this may handle Bluetooth connection, and this may handle USB connection. On top of that, there are firmware and software which initialize the components and help to manage their interaction. Say we want to send some data over the USB connection. First, the data is stored in hard disk. CPU then moves the data into DRAM. And then the USB controller gets the data by using direct memory access and send it over to the file component. And from there, the data is sent to the design. Now, say we want to model the tester to test this design model. Do we really want to model all the components, which by the way are complicated? Wouldn't it be easier if we just model the file component, and if we want to send data over, we create the data in the file component and send it to the design? In this way, we don't need to bother with the complexity of the other components. We don't need to model their interaction, we don't need to manage their timing, and we don't need firmware to initialize the components. Now, when the design cycle is over, there may be another design in development. There could be new features or modification to existing features. For example, it may be using USB 3 instead of USB 2, where these components need to be upgraded. Or maybe there is a new satellite connection, where new components need to be added into the system. This looks easy on block diagrams, but in reality, the old tester may not be able to support all these features, and therefore a new tester needs to be developed to work with the new design, and that is expensive. Now, as for the tester model, we don't want to redo the whole thing just because there's a new design. We want to be able to reuse the existing components as much as possible. If we are using class to model the components, we can use inheritance and polymorphism to change its behavior. And this would help in features upgrade modification. Imagine that this is the old test that we use for the old design, and when a new design comes, we want to be able to reuse this whole thing. And so that for the new features, we only need to add on new test components. Now let's focus on the model side. This is a design. It is usually written in module, and it has ports which allows you to communicate with it. To validate its functionality, we create a test, and in the test, we create components. Usually one component is responsible for one type of port. The test then can send a transaction to the components, and the component translates the transaction into signal activity which is sent to the design. In the test, components and transactions are modeled using class because class supports inheritance and polymorphism, which allow them to be reusable and overridable. Generally, this is a simple structural view of a test bench. While these block diagrams may appear simple, it takes a lot of consideration and high level of skill to create a test bench that is both reusable and extendable. UVM helps in two ways. First, it provides the base classes for you to use, and it provides standardization on how these classes can be used. To gain a better understanding of a UVM, it is important to understand these diagrams deeper. For example, components are equivalent of a design module. They are created at the beginning of time and they exist throughout a simulation. Transactions, on the other hand, are created when they are needed and they are destroyed when they are no longer in use. They are comparable to the signal activity. Now, once you've understand this concept, you'll be able to understand various UVM classes. And this is a simplified UVM class diagram. It starts with a UVM void, which is a dummy class and it doesn't really do anything. The next extension is UVM object. This is an important class. It contains functions such as copy, compare, and print, but we'll look into its detail in future video. From UVM object, there are two major lines of extension. This is to model instruction and sequence of instructions. It contains UVM transaction, UVM sequence item, UVM sequence base, and UVM sequence. This line of extension is used to model components. There are many kinds of components such as UVM test, UVM environment, UVM agent, and so on. As I was saying, if you can understand the structure of a test bench, you will be able to understand these class diagrams easier. Having said that, there are other classes and other lines of extension. For example, there's UVM resource, which is used to configure a test bench, and then there's UVM reg, which is used to model configuration status register of a design. If this is overwhelming, do not worry, we'll look into every one of these classes and more in future videos. Well, that's it for this time. Thanks for watching. I hope you find the video helpful. And do help supporting by clicking like, share, and subscribe.